All right, let's talk about two of the most important and maybe most confusing ideas in all of statistics: alpha and the p value. You've probably heard of studies' findings called statistically significant, right? Well, what does that actually mean? Stick with me, and by the end of this, you'll get it.
So, let's put this into a real world context. Imagine you're a scientist and you've just created a new drug that you think helps people recover from an illness faster. You run a trial, and the patients taking your drug do seem to get better quicker. But here's the big question: is that a real effect from your drug, or was it just random chance? That's exactly the kind of problem hypothesis testing was designed to solve. Now, the way we start is kind of counterintuitive. The very first thing we do is assume our drug does absolutely nothing. We assume the opposite of what we're hoping to prove. In stat speak, this is called the null hypothesis, or H naught. Think of it as the default, status quo position. Our whole goal is to gather enough evidence to show that this no effect idea is probably wrong. Okay, so what counts as enough evidence? Well, before we even peek at our results, we have to set the bar. We have to decide on our standard of proof. And that's where our first hero, alpha, steps in. Alpha, which you'll also hear called the significance level, is just a threshold. It's a line we draw in the sand before the experiment even starts. It's our pre-made rule for the whole game. It basically says, if the evidence we find is stronger than this line, then we're going to reject that no effect idea. So what's a typical line in the sand? Well, far and away, the most common value for alpha you'll see is 0.05, or 5%. What that really means is we're deciding upfront that we're willing to accept a 5% risk of being wrong if we claim our drug works. You see, no test is ever perfect, so we have to decide how much risk of a mistake we're okay with. And that 5% risk has a fancy name, a type 1 error. But honestly, just think of it as a false positive. It's the risk of throwing a party and announcing your drug is a miracle cure, when in reality, it did nothing and the null hypothesis was true the whole time. So by setting alpha to 0.05, we're basically capping our risk of that specific blunder at just 5%. And this image here shows you exactly what I'm talking about. See that bell curve? That little red area on the edge is what we call the rejection region. The size of that region is our alpha, our 0.05. We're saying ahead of time that if our result is so weird and so extreme that it lands in that unlikely red zone, we're going to have to reject our no effect theory. So, bottom line for alpha, it's all about managing risk. By setting alpha, we're putting a hard ceiling on our chance of making one of those false positive mistakes. We've set our standard. Now, let's go get the evidence. And that brings us to our second key concept. So, we've set the bar with alpha. Now we go run our experiment, we get all our data, and we crunch the numbers. And that process gives us one single value that's meant to summarize how strong our evidence is. That number, my friends, is the p-value. Okay, this definition is everything, so let's really unpack it. The p-value answers a very specific question. It asks, let's pretend for a minute the drug really has no effect. If that were true, what are the odds we'd see results as strong as the ones we just saw, just through sheer random luck? So here's how to think about it. A really, really small p-value means your result was super surprising. It would be incredibly unlikely to happen if the drug did nothing, and that makes you seriously doubt that whole no effect idea. But a big p-value, that means your result wasn't surprising at all. It could have happened easily by chance, so you've got no real reason to question the null hypothesis. Looking back at our diagram, see where it says p-value? It's pointing to that shaded area. That little sliver of space is the probability we calculated from our own data. The smaller that shaded area is, the further out into the tail a result falls, the stronger our evidence becomes. All right, so we have our standard of proof that we set beforehand. That's alpha. And now we have the strength of our evidence calculated from the data. That's the p-value. So what now? Well, now comes the super easy part, the verdict. We just compare them. The rule itself is just beautiful in its simplicity. If your p-value is less than or equal to your alpha, you reject the null hypothesis. That's it. Your evidence met or even beat the standard of proof you set for yourself. And that, right there, is what it means when you hear a result is statistically significant. It's not just a feeling or an opinion. It's the clear-cut outcome of this one comparison. It means your p-value, your evidence, was small enough to land inside that rejection region you mapped out with alpha from the very beginning. Let's wrap this up by quickly going over the key differences one more time, and then I want to flag one huge misunderstanding that trips people up all the time. So let's just lay it out plain and simple. Alpha is the rule you choose before you see the data. It's your cutoff. The p-value is the probability you calculate from your data. It's the observed evidence. They have totally different jobs, but they work as a team to get you to your final decision.
So if you remember anything, remember this. Alpha comes first. It's your risk tolerance. The p-value comes from the data. It's the strength of your evidence. And the smaller that p-value gets, the more you should be side-eyeing that initial no-effect assumption. Okay, please listen to this part. This is the single biggest mistake people make. Let's say you get a p-value of 0.03. This does not mean there's a 3% chance the null hypothesis is true. No way. That is completely, fundamentally wrong.
Let's say it one more time, just so it really sinks in. The p-value is the probability of seeing data like yours, assuming that the no-effect idea was true from the start. I know it's a subtle difference in wording, but in the world of statistics, that subtlety is everything.
And that brings us to one last really important question to chew on. Just because a result is statistically significant, does that automatically mean it's important in the real world? Not at all. Significance just tells you that an effect is probably real and not due to chance. It doesn't tell you how big or how meaningful that effect is. And telling the difference between those two things, well, that's the next step in really thinking like a scientist.